Okay, so how is everyone today? Good, I hope? Okay. Let's see. Is that better? No. Like this? Yeah, that's better. All right. So we've been discussing these concepts. A relation. A relation is a specific kind of function. No, backwards. A function is a specific kind of relation, and then we're also interested in specific kinds of functions. One specific kind of function is an injective function. Another kind of function is a surjective function. And then, if it is the case that it is both injective and surjective, then that's a special enough case that we have a special name for that. That's bijective. So, in particular, it makes no sense to ask, well, not all relations are functions. And if you have a relation which is not a function, it makes no sense to ask whether or not it is injective. In the same kind of way that I could put this up here, and I could say, please tell me, concerning this apple, is it a red apple? How would you respond? And then I say, oh, but it's clearly red. But of course, the problem is that it's not in the first place an apple. So the question of whether or not it's red is it is in particular a red apple is nonsense. Okay. So I'm going to make an analogy. So we are together going into business. And our business is the vending machine RS company. So it's our position that all of our vending machines should work. And furthermore, they should be there should be no surprises in the way that they work, right? Because we want to have no complaints, because complaints are expensive to deal with. Okay, so here's an example vending machine. So it has buttons 1, 2, 3. And it has candy bars A, B, C, and D. So I'll just say candy. Suppose that this is what the buttons do. When you press button 1, out comes an A and a C. When you press button 2, out comes a B. And when you press button 3, out comes a D. So since we're a vending machine company, and we want to have flawless vending machines, I claim that this vending machine has a defect. Its operation is confusing. What's defective about it? Right. Button 1 produces 2 outputs. That's not the way a vending machine should work. It should produce just 1 output. So the defect here, if you like, is that button 1 produces 2 candies. But we only want them to produce 1. just one output. So I'm going to change that just to exactly, but we want exactly one output for every button. Okay, now that's what you might say from a vending machine manufacturing point of view, but from a math point of view, that means that what is this vending machine not? It is not a function. So the defect with this vending machine is that it's not a function. Button 1 should produce just one candy bar, but currently it's producing 2 candy bars. So suppose that we send it back and say, all right, well, this vending machine needs to be reworked. And so it gets reworked in the following way. Someone looks at it and says, oh, I see the problem. The problem is that button 1 is producing 2 outputs. All right. So we'll rewire it a little bit and do the following and say, all right, now this is how it's wired. And the technician says, okay, I fixed it. Every button now has one output. So it's a function now. But it still has a defect. What's its defect now? Yeah. If you're going to display item C, then you need a button that will give you item C. But no item. No button produces item C. If you're going to display an item, you need to be able to get an item. So it's a function, but it is not what? Bijective. I agree it's not bijective, but which jective is it not? It's not surjective. A surjective vending machine means that every item on display can be obtained. If you have a vending machine that's not surjective, you're going to eventually get a complaint. Someone's going to call and say, hey, man, quit teasing me with that C on display there. That's what I want, but there's no button. Okay, so then we send it back. And do the following. So so the engineer says, okay, every item. Okay. So we have buttons 1, 2, and 3, and then some items in the display were removed, and things were rewired. Okay, great. So now it's a surjective function. So that's good. But I claim that this latest iteration of the vending machine has a defect. What's its defect? Right. Why is it that I can get a D candy bar in two different ways? It seems to me there should be just one way. It's confusing. Which one am I supposed to press? But two buttons, two different buttons, both produce item D. So it's a surjective function, that's great, but it is not what? It's not injective. It's not injective. Okay, but I do want to also point out, just as a little side item here, that if the engineer had done this instead, or technician, or whoever's given this person such a hard time, well, this particular one, it's a function, because every button yields just one candy. But this particular one is not surjective because B and C cannot be obtained, and it is also not injective because A can be obtained in more than one way. So this one is neither one. Finally, some clear communication is established between customer and the technician, and the following result is given. Okay, so how about this one? Is it a function? Yes, it's a function because every button does one thing. Is it surjective? Yes, everything on display can be obtained. Is it injective?
Because it's at most one.
At most one, right? So to be surjective is every item that's on display can be obtained with a button. Injective is that every item that can be obtained with just one button. So there is a way to get a C. There's at least one way, and in fact, there's exactly one way. So no buttons are duplicated, no inputs are duplicated, no outputs are duplicated. This is a correct vending machine. So it is a function which is injective and surjective, and therefore bijective. We're a vending machine company that in our estimation of vending machine worldview, the only correct kind of vending machine is a bijective one. Every button should do one thing. Everything that's on display should be obtainable. Every button should do just one thing. And when you have that, that's a correct vending machine. Any question about this? Okay, good. So we've said this a couple times, but I get emails from y'all, and some of y'all come see me in the office, and I get the sense that maybe making that analogy one more time in a slightly different way would be helpful. So now the question is concerning those terms. How do function injective and surjective look. On XY plots. So if you had a function and you plotted it, how could you look at the plot and say, oh yeah, that one's a function, and that one is injective, etc. Okay. So the question of, is it a function? So would you please remind me, what does it mean for a relation to be a function?
Every input has at least one output.
That's true of all relations. Right. Which means that every button does one thing. That's what it means to be a function. Not a function is you press button 3 and out comes 2 items. Not a function. So, every input, produces exactly one output. Well, I want to be clear, exactly one output. So to be slightly, there's a slight ambiguity here, and that is every input, and I'll say in the domain. And I have to say that because in principle there could be a vending machine over there, the side of the class, and I could say, hey, could you do me a favor and go tell me what happens if you press button number 8? And one of the things that could happen is you could come back and say, well, I looked at the machine and in fact there wasn't a button 8. So I can't press it. Okay. So there's a plot. And here's a plot. Okay. As a reminder, what these plots are, we're considering the horizontal axis to be the input axis. The buttons that you can press. And the vertical axis is the outputs. So, for this particular vending machine, if I were to say to you, hey, could you go over there and press button number -6? So maybe that's button number -6. It's not in the domain. So this, the way you can tell is you draw this line here and observe that that line doesn't have any intersections. Therefore, that input is not in the domain. No intersections. And therefore, that input is not in the domain. All right. Suppose that I say, oh yeah, sorry, I was mistaken. Actually, instead of pressing that button, I wanted you to press button number 5. So button number 5. Is that in the domain? Yes, it is. Because if you draw this, right here, there is an intersection. And therefore, that input is in the domain. So you first confirm it. He said to come over here and press button 5. Is there a button 5? There is a button 5. So now that I know that there is a button 5, I'm going to press button 5. So pressing button 5 is to say, oh, look, that's what happens, and it produces this output. So you press that input, and it produces that output. So this input produces this output. So, just eyeballing it, I said this was 5. There's no scale on this or anything, so, if I said that this is 5, then it appears to me that that's maybe 1. So you press button 5, and out comes a 1. All right. So the question that we're asking is, I put two plots in front of us, two vending machines, and the question is it the case for each one? Is it the case that it's a function? Well, what must be true in order for it to be a function?
Every input domain produces exactly one output.
All right. Is that the case for this plot? It is not, because, for example, concerning, say, this input. So is that input in the domain? It is, because the question of whether or not it's in the domain is, are there any intersections at all? So are there any intersections at all? Yes. And then, for a relation to be a function, it must be the case that everything in the domain produces exactly one output. How many outputs does this one produce? 2. So this produces 2 outputs. And therefore, for this specific example, the question of whether or not it's a function, the answer is no. Therefore, not a function. Okay. Now, to contrast it with this one on the right, notice that well, this one is not in the domain, so that's not a button. It's not in the domain. Okay. And this one, this input, is that input in the domain? Yes. And how many outputs does that input produce? 1. And then conceptually, if you consider taking this vertical line and moving it back and forth, can you see that there's always either 0 intersections or 1 intersection? As a result, what's the answer to the question, does this plot represent the plot of a function? The answer is yes. Okay, good. It's a function. That one's not. Okay, now, a different question is concerning a function. Is it injective? So again, with some plots, 3 this time. Is it injective? So, in terms of inputs and outputs, what is the, just like we wrote this phrase here, every input in the domain produces exactly one output. What do you say for, what is the correct phrase for injective? So every input produces at most one output is this one. What you need to do is you take this phrase and you have to switch the positions of the key words input and output. Yeah. So now it's every output and now, just like we said in the domain, so now it's every output in the image produces exactly one output. It is produced by exactly one input. Notice that these sentences are almost the same, except we just had to swap the positions of the words input and output. No. So the in the image predicate is what changes it. So if we changed it from in the image to in the range, then the answer would be, then it would be bijective. Well, don't worry, we'll get to it. That's 2 pages from now. So I have a question. So how about this output? So that's like maybe like a -6. I see that there's a -6 in that vending machine. Could you go over there and tell me which button you have to press so that we can get a -6? What button do you need to press so that you can get a -6? There is not a button. So notice that this horizontal line how many intersections does it have? Well, none. So this output has no intersection. And therefore, this output is not in the image. It's not in the image. All right. How about you come back and you say, well, actually, there's not a button to get a -6. And so then I say, all right, well then, could you tell me how I can get a 3? I see that there's a 3 over there on display. Can you get a? Is it possible? Is there a button that will produce a 3? Yes, and you can see that from this horizontal line. So this input, this output can be obtained. So this is produced by well, which output, or which input produces that output? That input. You press that button, and you get that one. So it's produced by this input. Okay, so, yep, you can get that one. Now, every output in the image is produced by exactly one input. Okay, so that means that, well, notice that, for example, it is possible to get this output, this like maybe negative half. You can get this vending machine to output a negative half. In how many ways? How many different buttons can you press? More than two. Three, right? Because of that. So notice that, in fact, there's three buttons. You could press that one, or that one. So this output that output right there is produced by three inputs. As a result, now we can finally answer the question that was posed about this plot. Is this the plot of an injective function? No. We can say that this is not injective. Not injective because of this, and that alone. That's why. We made these other nice observations, but that's just me being a teacher, right? It's enough to say, oh, look, there's one with three. So the answer is no. All right. So now let's do the same question about this one. So is it the case that, well, let's phrase this in a nice way. The test for injective is that every horizontal line should intersect at most once. 0 intersections down here, 0 intersections up here, 1 right there, so that's nice, but that one right there has 3 intersections. So 3 buttons that produce a Snickers bar. Nope, send it back. Okay, so if there's 0 intersections, that means that the output is not in the image. If there is an intersection, it means it is in the image. So is it the case for this middle one that every horizontal line intersects 0 or 1 times? Yeah. For the one in the middle, 0 or 1. Okay. So yes, this one is injective. Okay, what about this one? Is this one injective? I disagree. Now, you might say, here's a different question, which is, I think, the question that you answered. But this is not the question that I asked. Is it the case that every horizontal line intersects this plot 0 or 1 times? Yes, that's true. Because down here you can see 0 intersections. There's 1, 1, 1, 0. So, to the question, is it the case that every horizontal line intersects 0 or 1 times? Yes. Yet, the answer to the question of is this an injective function is no. Why not?
It's not
It's not a function. So it's surely not an injective one. Why is it not a function?
Because more than one.
Yeah, that's why. So the answer is that this is not this last one is not injective. Because it's not a function. Right? So like you can see right there that it's not a function. It's the same. So what I want to point out to you is that it is in a way nonsense to ask if this one is an injective function because it's not in the first place a function. Just like it's nonsense for me to say, concerning this apple, is it a red apple? And of course, the answer is, if anything, no, because it's not in the first place an apple. All right. So I want to make it clear to you that there's two questions. So I'm going to draw a table here. So the first question, the first statement is every horizontal line intersects at most once. Now I'm going to turn the page 90 degrees and write the question every vertical line intersects at most once. Now, concerning these statements, each of them, there's only two possibilities. They are either false or true. So this could be false or true, and this one could be false or true. As a result, when considering both of those statements simultaneously, there's exactly 4 possibilities. The case when they're both false, they're both true, or you have 1 and 1. So a picture that corresponds to each of them. In the bottom right, that means that we need it to be the case that every horizontal line intersects at most once, that's true, and every vertical line intersects at most once. Here's an example. There's a question we can ask, is it a function? Is it a function? The answer is yes, because it passes the vertical line test. Because it's a function, we can go on to ask, is it injective? And what's the answer? Yes. Because it passes the horizontal line test. In the bottom left, so we can ask the question, is it a function? So is it? The answer is yes, because the test for that is the vertical line test. Because it's a function, we can go on to ask, is it injective? And what's the answer? No, because of the horizontal line test. And when you say no, I need you to visually indicate your reason. Right? So, for example, right here. Not injective. In the top right, it's just like the bottom left, except I turned it sideways. And we can ask the question, is it a function? The answer is no. And what test confirms that response?
Doesn't pass the right test.
Very good. So because we're saying no, we need to visually indicate the no. Okay. Then, on a, when this question comes up, I'm also going to say, well, is it injective? And what's the correct answer? Right. So the answer is no, because it's not a function. And in a real sense, it makes it's nonsense to ask if it is injective. But I need you to tell me that you understand that it's nonsense. Right? Finally, something that is that fails both would be what? How about a circle? A circle would fail both. But you can be a little bit artistic and do something like this. How about beautiful, right? So, is it a function? No. Because, for example, this one. And then, is it injective? No, because it's not a function. Those are the only 4 possibilities. Every question that I ask is going to have to be some variation on these 4. But what I'm telling you is that inevitably what happens is the students mess up this one. Because the statement, every horizontal line intersects at most once, is true. But that doesn't mean it's injective, because it's not in the first place a function. Good. Any question about this? Okay, finally. I'll say let f of x be the square root of x. So a function defined by the expression square root of x. What's the domain of this function? Well, in the interest of time, I'll remind you of the rule. The rule is that when the domain is not explicitly stated, the domain of the function is the domain, the natural domain of the expression. So now, that's in contrast to if I had said, let f of x be the square root of x on domain 50 to 100. In such a case, the answer would be that the domain is 50 to 100. That'd be the answer. But we didn't say it, so as a result, the domain for this function, the domain is the natural domain of the square root of x, which is x greater than or equal to 0, written as an interval that's 0 to infinity, and written as a plot like so. Okay. That means that for the square root vending machine, if you make an order for the square root vending machine and you don't specifically say what buttons you want, then every button from 0 to infinity is going to be installed. They're all going to be put. Then, what's the range? Well, again, in the interest of time, I'll remind you of the rule. Is that when the range is not explicit, the range is the reals. So I didn't, when I said let f be given in that way, and I didn't say anything about the range, that means that the range for this f is the reals. Again, to make a vending machine analogy, it's saying that, well, if you order the square root of x vending machine, and you don't specifically say what you want to be displayed through the glass, then everything is going to be in there. Every single thing. Okay? But there's a separate question of what's the image? Now, the image is the set of items that are on display that you can actually get with a button, right? Because it might be the case that something that's in there that you can see plainly, but there's no button to get it. So this is the set of obtainable outputs. Which are in the range. Well, the best way to go about doing this, at least for now, is let's figure out what it looks like with a plot. X here and f of x here, so 0, 1, 2, 3, 4. So I'm kind of rushing because the clock is against us. So if you give input 0 to the square root of 0 is 0, the square root of 1 is 1, the square root of 2 is about 1.4, the square root of 3 is about 1.7, the square root of 4 is exactly 2. And we could go on and do some more, but that'll be enough for now. So the domain, we said, is 0 to infinity. So just this much is the domain. Those are the buttons that are installed. The range is all reals. So the range is all of this. All of these things are on display. When you plot these points, you will see the following. Something like that. So the image is the set of obtainable outputs in the range. So is this in the image? No. It's on display, but you can't get it. What about, is this one in the image? Yes. Yes. So the reason why this one is no is because, notice that there's no intersections with this line. The reason why this one is yes is, well, because there is an intersection. So what is the image for this function? So no, yes, right? That's the first one you can get. And then do you observe that you can get all of them from that point on? As a result, what is the image? 0 to infinity. Now, it's just a coincidence that the domain and the image are the same. That need not be the case. But what I am saying is that this is the image, all of this, and all of everything is the range. Very good. So what we're going to do next time, this is one function. What we're going to do next time is we're going to make a catalog of functions, and we're going to know what their domains are, we're going to know what their images are, and what their plots are, so that we have like a catalog of what they should look like and who's who. Finally, the last thing I want to leave you with is that near the beginning of the semester, I asked a question like, what's the square root of 9? And some of you said 3, and some of you said plus or minus 3. And I said, no, it is just 3. And I agree entirely that when you square 3, you get 9, and when you square negative 3, you get 9. Nevertheless, the square root of 9 is 3, and not plus or minus 3. Because to be a function, how many outputs are permissible for a given input? 1. As a result, the square root of 9 is 3. Not plus or minus 3, because that would be saying that when you press button 9, out comes 2 items. But we insist that the square root be a function, not a relation. As a result, the square root of 9 is 3. Good. I hope you have a nice Wednesday.